did 3 questions for homework last night on your Projectile Motion 2 worksheet. It was questions 1 to 3. We'll give you some answers for that right now, and then we'll take a look at a couple of them if we need to do that. The answer for number 1 is 141 meters. Number 2 is 10 meters. And number 3A, we get 4.4 seconds. And 3B is 55 meters. Any issues with any of those 3 questions that you'd like to go over here, Bree? 2 and 3? Okay, let's take a look at 2 and 3 here. My gut is, Nathan, if we can do 2 and 3, we're probably going to be okay with number 1. But in the end, if there's a problem with that, still after we're done going over 2 and 3, we'll go over number 1 then. Okay. Okay. 2 says a golfer is teeing off on a 170-meter long par 3 hole. The ball leaves with a velocity of 40 meters per second and an angle of 50 degrees with respect to the ground. Assuming that she hits the ball on the direct path toward the flag, how far from the flagstick is the ball when it strikes the ground? This is a good question because it's kind of a recipe-based question, like most projectile motion questions are, but then we have to think a little bit at the end. We get a number here, and it's not the number we want. It's not the answer that we want. So we got to figure out at that point what we have to do to get the answer that we want. So the first thing that we want to do here is draw this out. We have this golf ball that's launched at an angle of 50 degrees with respect to the ground at a speed of, or at a velocity of 40 meters per second. We know that the ball is going to go up like this, come back down like this. What's the shape of that path called? Yep, Sam? It's called a parabola, right? Now, a lot of times we look at this and say, boy, we don't have enough information. We have information about how it starts, but that's it. That's okay, because in the end, you think about it. What determines how far this ball goes? The starting conditions, how fast it's hit, and the angle at which it's hit, along with gravity, which we know is 9.81. Now, other people are going to look at this and say, wait a sec, we do have one more piece of information here. We have the displacement of the ball. It's 170 meters long, but it's not. It says that's how long the hole is. It doesn't say that's how far the ball goes. We don't know what the displacement, the horizontal displacement of this ball is. So let's not write it in. Let's ignore that 170, at least for now. Let's break it up into, let's break the 40 meters per second up into the x and y components, because we don't like funny angles. We got x component here, we got y component here, 40 meters per second here, and an angle of 50 degrees. Cosine 50 degrees is equal to adjacent over hypotenuse, and sine 50 degrees is equal to opposite over hypotenuse. What does the x component work out to be there? 40 cos 50. 25.7 meters per second. And the y component, 40 sine 50, works out to be 30.6 meters per second. All right. If we want to, we can replace this one vector with those 2 vectors. I'm going to leave it this time because a lot of you don't do that. So I'm just going to do it your way this time. In the end, visualize it that way, though. Visualize it like, look, this 40 isn't there anymore. We got an x of 25 and a y of 30. Okay, the x component can be described always by this equation. A number of people came in today and asked me for help on these questions. That's good. Listen, if you're struggling with these questions, come and ask me questions, please. Here's the thing. Here's what a lot of people think. Oh, I don't want to go ask questions because he's going to think I'm not very smart. Well, A, if you don't understand this, it doesn't mean you're not very smart. B, we have a test on Thursday. Would you rather me find out now that you don't know it, or would you rather me find out Thursday that you don't know it? Because I'm going to find out. It's either now or Thursday. Let's make it now. If you're having trouble, come in for help so we can get this fixed before Thursday. Because I'm going to find out anyways if you don't understand it. V equals d over t for the x component. D is equal to VIT for the y component plus 1/2 AT squared. Those people that came in to ask me questions about this, a lot of people didn't have these 2 equations written down. They said they didn't know what to do next. We always know what to do next. This isn't the thinking part of the question. This is the do the same thing every time part of the question. This is you're going to the bathroom, okay? You don't have to think about what to do first. You lift up the lid, okay? We do it every single time, exactly the same way every single time, okay? You don't have to think about it. It's routine. It's the exact same thing every single time to this point. Now, this is when it gets a little bit trickier, though. Okay? This is when sometimes a lack of understanding can come into play here. Fair enough. What do we replace v with for the x component here? What do we replace v with, Sam? Pardon me? No. We're not ever using that 40 meters per second again. Remember, we don't like funny angles. We got rid of the funny angle along with the 40 meters per second, so we're never going to use that again. It's as if it's not there. Remember what I usually do is erase that 40. It's gone, right? Chantal? 25.7 meters per second. Good. It's the x component of that velocity. Now, delta d for the x component we don't know, and nor do we know delta t. So we get an equation there with two unknowns. Not very helpful yet, but odds are it's going to be helpful before I'm finished here. Now the y component. Do we know what delta d is for the y component, Tegan? It goes up from ground level. It comes back to ground level. Up and down, what's the change in position? Yes, good, 0. It doesn't land on top of a building 20 meters above where it started. It doesn't end up at the bottom of a cliff 10 meters below where it started. It ends up on the same level. Horizontally, it's moved. Vertically, it's moved. It's covered a distance vertically. But displacement, if it ends up back where it started vertically, then its displacement is 0. It's like running around the track, right? I think on first or second day of class this year, we use that example. You run around the track, you end up where you started, your displacement is 0. VI for the y component. VI for the y component. Karsten, what's VI for the y component? Good. 30.6 meters per second times the time plus 1/2 of a, which is -9.81 times the time squared. Now, we can divide everything by t. And we're left with 0 is equal to 30.6, subtract 4.905, that's 1/2 of -9.81 times t. The 4.905, we'll take it to the other side by adding, so it becomes positive 4.905 equals 30.6. And we do the math there, and that should work out to be a time of, what, is it 6.2 seconds-ish? Cassie? 6.2? Which now we're going to turn around and plug that back into there. How come we can switch time from y to x? So that's this question about 3 or 4 times already, but you guys know this now, right? How come we can put the y time into the x time? Because time doesn't have direction. Good. So 6.2 times 25.7 should give me, should give me 160 meters. It's not my answer. I told you it was 10 meters. What do we do to get 10? Why do we do it, Chantal? Good. The 170 was irrelevant up until now. It had nothing to do with how far the ball traveled. That's just where we wanted to put the ball. Well, we didn't put it there. We put it 160 meters down the course. Well, if the hole is 170 meters from where you shot, and you shot at 160 meters, then that means you're 10 meters from the pin. That means you're going to subtract 170 minus 160. That's how far the ball lands from the hole. Okay? Any questions about that before we move on to the next question? Number 3 says, the punter in a football game, the punter is the person that kicks, right? Kicks the ball. The punter in a football game kicks a high, booming kick from his own goal line, or from her own goal line. He or she kicks the ball at a 60-degree angle with a velocity of 25 meters per second. What's the hang time? Now, if you're not a football fan or a sports fan, you might not even know what hang time means, but they tell us. They tell us that hang time is how long the ball was in the air for. Sometimes you want a long hang time when you're kicking a football. Give your guys a chance to run under the ball, right? To catch up to the offense before they actually go anywhere with it, so you can tackle them right away. And sometimes you might want a short hang time, depending upon the situation. We also want to find out how far downfield it lands. Here's the football. It's kicked in a parabolic path like this at a speed of 25 meters per second and an angle of 60 degrees. We don't like funny angles, so off to the side, we get rid of that. 60 degrees, 25 meters per second. And we label this as X and label this as Y. We're going to say cosine 60 degrees is equal to adjacent over hypotenuse. I think that works out to be 12.5 meters per second. Thank you. And the Y component, that's going to work out to be 18.99. All right, 21.6. We'll go with that. You sound more confident than I sounded, so we'll go with 21.6 meters per second. Now, if we want to, we can replace this, right? Let's do that this time, since somebody made a mistake last time with giving us our X and our Y component here. We've got an X component of 12.5. We've got a Y component of 21.6. Now, let's break it up into those X and Y components. Hey, you got to do the same thing every time, right? It's instinctual. It's like the bear in his den who in the springtime wakes up every spring. Doesn't have to think about it, just wakes up and goes out looking for food. He does the same thing every time, right? Every spring does the same thing. We're going to do the same thing every time with this question. X component, Y component, d over t for the X, and VIT plus 1/2 AT squared for the Y. No exceptions. Now, for the Y component, you may find that you have to use another equation other than that one. Not very often, but I still want you every time to try that one first, because it's the one that's going to work 95, 98% of the time. So try it first. D over T, it always works. Sam, what's the X component of the velocity there? Good. 12.5 meters per second. Let's plug it in. What is delta D? We don't know that one, do we? We don't know delta T either. What's the Y displacement? What's the Y displacement for this one? Megan, what's the Y displacement? Is it starts at ground level and comes back down to ground level? Good. So let's plug in 0 for that. VI for the Y component. VI for the Y component is, Terry, what's VI for the Y component? No, it was launched at 25 meters per second. How much of that 25 was a Y component? No. You're close, though. You're getting closer. 21.6. Thank you. Delta T is unknown. Now we're getting to the point where we've done this enough times, we can just cross off this if we want. Really what we're doing there is dividing every term by T. But if you don't want to show that, that's okay at this point. So half of negative 9.181 is negative positive 4.905. Negative, but we're going to take it to the other side by adding. That's going to be 4.4-ish. What is it? 4.4 seconds. We're going to plug it into here. 12.5 times 4.4 gives us a displacement for question number 3 of 55 meters. So we've just solved both now, right? Time of 4.4 seconds. The time of 4.4 seconds was the hang time. That was question A. And how far downfield it goes is 55 meters. That's question B. Make sense? The one thing that was not asked of you in any of these 3 questions that you had for homework last night, what's the maximum height? What's the maximum height of this ball? Any suggestions to find the maximum height? We did that, I think, with one question yesterday. We will do it on the test. You will be asked for maximum height on the test. How are we going to find it? For the y component, you mean? Yes. If we're analyzing only the trip up, right? Right. If we're analyzing the trip up and not the trip back down, so in other words, not the whole thing, but only half of it, then VI is 21.6 and VF is 0. Good. And then we're going to find the displacement there, right? The displacement when it stops vertically. Horizontally, it always keeps going at 12.5 meters per second, but vertically, it does actually slow down and stop, and then reverse direction and speed up again. So let's analyze the y component, the trip up for the y component. It's going to look something like this. Vf squared is equal to Vi squared plus 2AD. We're going to say 0 is equal to 21.6 squared plus 2 times neg 9.81 times D. 2 times 9.81 is 19.62. It's negative, but we'll take it to the other side by adding. 21.6, square it, and then divide it by 19.62, and we're going to get the displacement then. I'm going to say it's 20-something. I'm going to say 24. Anybody have it? So the idea is 24 meters. Is that okay? You guys think you can find max height? Let's give you a relatively short outline for your unit test now that we have coming up tomorrow. Thursday, I mean. Yeah, Thursday. If you remember back to the very beginning of the unit, we start off by talking about vectors and scalars. We have to know the difference between a vector and a scalar. We have to know what each of them are. Right? A scalar has only magnitude. A vector has both magnitude and direction. And we have to know examples. Maybe you get a question that says, the following are examples of vectors. Option A, B, C, and D. And you got to fill in which one has all examples of vectors, or scalars, or which one are not vectors, or which ones are not scalars. If it's got magnitude and direction, it's a vector. Now, I'll let you in on a little trick here. If you're studying for this test and then you come in and you write the test and there is a question like that and you forget, oh my goodness, I forget whether acceleration is a vector or a scalar. What's a way to cheat without cheating? That's kind of an oxymoron, but what's a way to cheat on that without cheating? Yeah, go to your data sheet. Find acceleration. If it has a little arrow over top of it, it's a, right, and if it doesn't, it's a scalar, right? It's not cheating, guys. If I give you that data sheet for the test, that's not cheating. That's taking advantage of the resources that I give you. I'd like you to know that acceleration is a vector, but if you don't, as long as you can find out with what I give you, then that's okay. So know what it is, know some examples, and that's probably about it for vectors versus scalars. And then we learned some kinematics terms. Some of these the first day of class, the rest, almost all the rest of them on the second day of class, and then one of them we learned a week or so later. Our terms were distance, position, displacement, time, speed, velocity, and the last one, which we didn't do at the same time as we did the other ones, but now we've done it, acceleration. What do you got to know about these? Well, you got to know what they are, okay, the definitions of them. I'm not going to ask you on a test to find distance for me. or define acceleration for me. I won't ask you that, but you need to know the definitions so that you can understand what they mean, right? So that you can find them, so that you understand when you're asked for position or you're asked for distance or displacement, you know the difference between, you know which one you really should be solving for. So you need to know definitions. You need to know vector versus scalars. You need to know equations for them, although you can always check your data sheet for the equations. And you need to know units. So this is basic stuff at this point, right? Basic stuff at this point. Just kind of the foundations of what we did. This is not the bulk of the test, what you see here right now. It's the foundation for the bulk of the test. Well, then we went on to look at our Group A problems. And basically our Group A was V is equal to d over t, constant velocity. I'm going to make one little point here. Remember this. This is what we did on the first and second day of class, and a lot of you had a little bit of trouble with. When you're finding displacement, and we need to find displacement in order to get velocity, right? We need delta d to solve for v. When you're finding displacement, you can find it in two ways. We can subtract positions, df minus v di. If we're given the position at 2 moments in time, subtract them. If you're given displacements, we're going to if we're given where we are now and then, we're going to subtract the two. If we're given how far we've traveled now and then how far we've traveled again, then we're going to add them, right? When you find a displacement, add displacements, subtract positions. Now, that's not this equation per se, but it's kind of a foundation for using that equation. You can't do v equals d over t if you don't know how to get d. Sometimes you've already got the value of d given to you, but sometimes you don't. Then we looked at position time graphs. We got the shapes of the graphs. Okay? When you see a straight line on a graph that slopes upward, know what that means. When you see a curved line, know what that means. The shapes of the graphs. And of course, our calculations. There's a number of things that we could find from a position time graph. Position, go up and over. Displacement, which is the change in position. Velocity, speed, average velocity. All kinds of things that we can find from that position time graph. Then we had our Group B problems. And this time when we do Group B, I'm going to include with that gravity. We separated those as two separate topics when we went through it because I didn't want to overwhelm you all at once. But now we're capable of solving any Group B problem where it doesn't involve gravity or where it does involve gravity being negative 9.81. And remember, for the Group B, there are 5 equations. On your data sheet, there's 6 equations in the first unit under kinematics. The first equation is Group A, v equals d over t. The rest of them are Group B. Just remember that we can use all of those when we're dealing with acceleration. Then we have velocity time graphs. Of course, we had shapes and we had calculations. When I give you your practice test, you're going to see that there's an example of a position time graph and a velocity time graph on that practice test. They're going to look almost exactly the same. The only difference, the y-axis. The shapes are the same, the numbers are the same, the x-axis is the same, the y-axis is different. Same numbers on the y-axis, different variable. You're going to think, some of you are going to think, oh, I can pretty much copy my answers from the first one, put it on the second one. No, you can't. Okay, things are completely different. It's not the shape of the graph that determines what you do. It's what's on the y-axis that determines what you do. So remember, know what the shapes of both position and time and velocity time mean, but know how to deal with them too. Know how to find things from them. And don't get the two mixed up. Then we did vector addition. Okay, be able to deal with right angles, which those are the easy ones, but also be able to deal with funny angles. And remember these 5 words. And whenever you see a funny angle, remember, I don't like funny angles. Get rid of it. So if you got 3 funny angles in the same question, draw 3 little asides and get rid of those funny angles. And just turn it into 90-degree things. 90-degree vectors, which ultimately you make a 90-degree triangle out of. And we did relative motion, which was what the quiz was today. I'll put in brackets there, navigation. And finally, we did projectile motion. Don't quote me on this because I haven't looked at the test in a little while here. But I believe there are a couple projectile motion questions on the test. One that's launched horizontally off the edge of the building, where all the initial velocity is x component. And then another one where it's launched at an angle, where you have to find how far downfield it goes and the maximum. That's it. That's our unit. So we take a look at this and think, that's not really that much, is it? It's a bit, but here we've been going for over 4 weeks here now. I think we're okay with this. You got 2 days before your test. Go back and review all this stuff. Use this as a little bit of a checklist. Put a check mark beside the term when you think you know it. Then do some practice problems with that term to see if you can keep that check mark there or if you have to cross it off and go back and do it again. There's a few questions that I'd like you to work on tonight, just as practice, and you can work on them for the next about 10 minutes of class here. They go along with the projectile motion stuff that we've been working on. It's check and reflect, page 112, number 1 to 9. I'm also going to hand out to you right now your practice exam. This is not homework. This is not formal homework. In fact, because there's going to be so many of you missing tomorrow, I'm not positive what we're doing yet, but there's a good chance that those of you who are here will have a chance to work on that practice test. Okay? Please, though, even though I'm not assigning it as formal homework for tomorrow, please do it for yourself before Thursday. I'll post the answers. Okay? I'll post the solutions to that. So even for those of you who aren't here, you're able to go back and look at the solutions to see, A, if you got the right answer, and B, if you didn't, what you did wrong. And if you have questions beyond that, feel free to come and see me.